Welcome back, students. So our topic is scattering of light. So in class 9 you studied about Tyndall effect. When light passes through a colloidal solution, its path can be visible. That is known as Tyndall effect. Okay. So scattering of light. That's page number 195. You have to write the questions and mark the answers in the textbook itself. Okay. So the interplay of light with objects around us give rise to several spectacular phenomena in nature. The blue color of the sky, the color of water in deep sea, the reddening of sun at sunset and sunrise are some of the wonderful phenomena we are familiar with. In previous class, we have learned about the scattering of light by colloidal particles. The path of light passing through a true solution is not visible. However, its path becomes visible through a colloidal solution where the size of the particles is relatively larger. In true solution, the size of the particle is very small, so it will not scatter the light. But in colloidal solution, the size of the particles are very large and it will scatter the light. So the path of the light is visible to you. That is Tyndall effect. Tyndall effect. The Earth's atmosphere is a heterogeneous mixture of minute particles. These particles include smog, tiny water droplets, suspended particles of dust and molecules of air. When a beam of light strikes such fine particles, the path of the beam becomes visible. The light reaches us after being reflected diffusely by these particles. The phenomena of scattering of light by the colloidal particles give rise to Tyndall effect. This phenomena is seen when a fine beam of sunlight enters a smoke-filled room through a small hole. The scattering of light makes the particles visible. Tyndall effect can also be observed when sunlight passes through a canopy of a dense forest. Here, tiny water droplets in the mist scatter the light. So, scattering of light is a phenomena of change in the direction of the light when it strikes on particles like molecules, dust particles, water droplets, etc. So, that is scattering of light. It will change the direction of the light ray when it strikes on the molecules of water, dust particles, all those things. Tyndall effect means due to scattering of light, the path of the light will be visible to you. Its path becomes visible to you in a colloidal solution where the size is comparatively larger. So, the phenomena of scattering of light by colloidal solution give rise to Tyndall effect. Means the beam of the light or the path of the light is visible to you when light passes through a colloidal solution. That is known as Tyndall effect. You can see the suspended particles of in air when sunlight enters a room through a small opening in the roof. Through a small glass which is placed on the roof, you can see the particles suspended in the air, or you can see the path of that light beam. That is known as Tyndall effect. So, here scattering of light depends upon two factors. First one is the wavelength of the light and second one is the size of the scattering particles. So, scattering depends upon two factors. First one is the wavelength of the light used, and second one the size of the scattering particles. The color of the scattered light depends on the size of the scattering particles. The color of the scattered light depends upon the size of the scattering particles. Very fine particles scatter mainly blue light, while particles of larger size scatter of longer wavelengths. If the size of the scattering particle is large enough, then the scattered light may even appear white. So, it depends upon the wavelength of the light and the size of the scattering particle. If the particles are very small, it will scatter the blue side region of the visible ray, means shorter wavelength region. Okay, shorter wavelength region. If the particle size is larger, then it will scatter the longer wavelength region, that is yellow, orange and red, or towards a red region. It will scatter longer wavelength. If the particle size is even larger, then the scattered light may even appear as white. Now, why the color of the sky appears blue? The molecules of air and other fine particles in the atmosphere have size smaller than the visible light. These are more effective in scattering of shorter wavelength at the blue end than the longer wavelength at the red end. The red light has a wavelength about 1.8 times greater than blue light. Thus, when sunlight passes through the atmosphere, the fine particles in the air scatter blue light shorter wavelength more strongly than red. The scattered blue light enters our eye. So, the sky appears blue in color. So, the atmosphere will scatter blue light more than red light, because the size of the particles in the atmosphere is very small. So, it will scatter shorter wavelength light, that is towards the violet, indigo, blue side. So, it will scatter more shorter wavelengths light, and that blue light enters our eye. So, we will see the color of sky as blue. If earth has no atmosphere, there would have been no scattering, then the sky would appear dark. The sky appears dark to a passenger flying at high altitudes. The scattering is not prominent at such height. So, if atmosphere is not there, then the sky appears black or dark in color. The same thing for a person who is traveling in higher altitudes. In that case also, the scattering is not prominent at higher altitude, because the density of the atmosphere goes on decreasing as we go away from the earth surface. So, the scattering is not prominent at higher altitudes. So, the sky appears dark to a person who is traveling at higher altitudes. Black color of sky in the absence of atmosphere. If there would have been no atmosphere, then there would be no scattering of light. No scattered light would reach our eye, and the sky appears black instead of blue. Since there is no atmosphere on moon, there is no scattered light reaches the moon's atmosphere. Hence, to an observer on the surface of the moon, no light reaches the eye of the observer except the light reaching directly from the sun. Thus, the sky in the direction other than that of the sun will appear black to an observer on the moon surface. Similarly, when an astronaut goes above the atmosphere of the earth in a rocket, he sees the sky black, but to him the earth appears blue due to the blue color of the sunlight scattered by the earth's atmosphere reaching him. The stars and other heavenly bodies are seen as usual but not twinkling. Okay. So, you may have observed that danger signals are red in color. What's the reason? Because the wavelength of red is more, about 700 nanometer. So, it will be least scattered by the molecules or the particles in the air. That's why danger lights are red in colors. Red is least scattered by fog or smoke. Therefore, it can be seen in the same color at a distance. It can be seen in the same color at a distance. Danger light, red light for danger signal. In the visible light, the wavelength of red light is longest. Therefore, the light of red color is scattered least by the air molecules of the atmosphere. Hence, the light of red color as compared to the light of other colors can penetrate to a longer distance without being weak, without becoming weak. Thus, red light can be seen from the farthest distance in comparison to the light of other colors having the same intensity. Hence, red light is used for danger signal so that the signal may be visible from a far distance even in fog, etc. Now, white color of clouds. The clouds are nearer to the earth's surface and they may contain dust particles and water molecules of size bigger than the wavelength of the visible light. The wavelength of visible light is from 400 nanometer to 700 nanometer. Therefore, the dust particles and the tiny ice particles present in the clouds scatter all colors of incident white light from the sun to the same extent, and hence when the scattered light reaches our eyes, the clouds are seen as white. So, clouds are seen as white because the size of the particle is larger than the wavelength of the visible light. So, it will scatter the white light coming from the sun equally. So, the clouds appears white to us. Therefore, the dust particles and the tiny ice particles present in the clouds scatter all the colors of incident white light from the sun to the same extent, and hence when the scattered light reaches our eye, the clouds appears to be white in color. Blue color of sky. The light from the sun has to travel a long distance on the earth atmosphere before reaching us. As the light travels through the atmosphere, it gets scattered in different directions by the air molecules present in its path. The blue light, due to its shorter wavelength, is scattered more as compared to the white light of longer wavelength. Thus, the light reaching our eye directly from the sun is rich in red color, while the light reaching from the eye from all other directions is a scattered blue light. Therefore, the sky in direction other than the direction of sun is seen blue. Further, after sunset and before sunrise, there is no sunlight reaching directly to us. Then the blue scattered light makes the entire sky to appear blue. So, sky appears blue, clouds appears white in color. If atmosphere is not there, then there will not be any scattering, then the sky appears black or dark in color. Then red color of sun at sunset and sunrise. At the time of sunset and sunrise, the light from the sun has to travel a longer distance to the atmosphere to reach the observer. During the morning and the evening, the sunlight has to cover a longer distance through the atmosphere to reach our eye. Since the blue color of shorter wavelength is scattered more and much of it is lost, while the red color of longer wavelength is scattered a little, so it is not much lost. This blue color is almost absent in sunlight reaching the observer, and only red light reaches us. As a result, the region near by it appears to be red. The diagram is given in your textbook, page number 197, figure 11.12. At the morning and the evening, the sun is near the horizon, so the sunlight has to travel more distance through the atmosphere to reach our eye. So, the shorter wavelength portion, that is violet, indigo and blue, will be scattered away, and only the longer wavelength region, that is orange, yellow, orange and red, will be left in the light from the sun, and that reaches our eyes, and we will see it as reddish orange color. Reddish orange color at the sun at the time of sunset and sunrise. At the noon, the sun is just above our head and it appears to be white in color. At the noon, the sun is just above our head and it appears white in color. At noon, the sun is directly above our head, so we get the light rays travelling from the sun. After travelling, we get the light ray directly from the sun after travelling shortest distance without much scattering of any particular color. Hence, the sky appears to be white in, hence the sun appears to be white in color at noon. So, at noon, the sun is just above our head, so it will cover, the sunlight has to cover a shortest distance. So, the scattering is not prominent there, or without much scattering of any particular color, it reaches to our eye. So, the sun appears to be white in color at noon. So, all these things are about the applications of scattering. So, if any question is there related to color, why the sky is red in color at the time of sunset and sunrise, means the area near to the sun appears to be red in color. At the time of sunset and sunrise, the sun appears to be white in color at the noon. Danger lights are red in color. Fog lights are yellow in color. Why fog lights are yellow in color? Yellow light is the most sensitive color to our human eye. Yellow light is the most sensitive color to the human eye. So, scattering will be less, but it is most sensitive color to our eyes. Danger lights are red in color. The sky appears blue in color. Clouds appears white in color. All those things are the applications of scattering of light. So, scattering means there will be a change in the direction of the light ray when it passes through the atmosphere, that is when it strikes molecules of dust, air or water droplets. So, scattering depends on two factors, wavelength of the light and size of the particles. So, if the size of the particle is very small, it will scatter mainly shorter wavelength region. If the particle size is larger, it will scatter longer wavelength region. If the particle size is very much large, then it will scatter all the light equally and it appears to be white in color. Okay. When activity is given in your textbook, page number 196, that is the scattering of light in a colloidal solution. So, what you have to do is that you have to place a strong source of light and at the focus of a converging lens. The lens provide a parallel beam of light. Allow the light beam to pass through a transparent water tank, glass tank containing clean water. Allow the beam of light to pass through a circular hole made in a cardboard. Obtain a sharp image of the circular hole on a screen using a second converging lens. Dissolve about 200 gram of sodium thiosulfate in about 2 liters of clean water taken in the tank. Add about 1 to 2 ml of concentrated sulfuric acid to the water. Observe what you can see. You will find that fine microscopic sulfur particles precipitating in about 2 to 3 minutes. As the sulfur particles begin to form, you can observe the blue light from the three sides of the tank. Means it will scatter shorter wavelengths. Okay. So, size of the precipitated particles is very small and it will scatter shorter wavelengths of the visible region. This is due to the scattering of shorter wavelength by minute colloidal sulfur particles. Observe the color of the transmitted light from the fourth side of the glass tank facing the circular hole. It is interesting to observe at first the orange red color, then bright crimson red color on the screen. This activity demonstrates the scattering of light, which may help you to understand the bluish color of the light and the reddish appearance of the sun at the sunrise and sunset. Okay. So, blue color of the sky will be seen. On the screen, you will be able to see a dark red color spot will be there. That means that is represented by the reddening of sun at the time of sunset and sunrise. Okay. So, that red color means it will scatter, the solution will scatter the longer wavelength region. Okay, the notes I will give. No need to write the notes. Just mark the points in your textbook. Okay. Thank you.